Self-inductance is a measure of the ability of an object to store magnetic potential energy in the form of a magnetic field. Self-inductance is a function of only the geometry describing the storage of the magnetic potential energy. Specifically, it is a function of the distribution of moving electric charge or electric current that creates the magnetic field. A material with a large self-inductance stores more magnetic potential energy at a given current than a material with low self-inductance. We refer to any material that has self-inductance as an inductor. This is the equation for self-inductance. It depends upon the rate of change of the current flowing through the inductor and the change in electric potential between the two ends of the conductor. Let's focus on a perfect solenoid as our example for understanding self-inductance. When the current in the solenoid changes, an electric field is induced. This induced electric field creates a separation of electric charge in the solenoid. As with capacitors, this separation of electric charge creates an electric field that can be associated with energy storage. We can determine the induced electric field from the change in magnetic flux through the solenoid, or from the derivative of the magnetic potential of the solenoid. This derivative is straightforward since only the current depends upon time. This induced electric field creates a separation of electric charge in the solenoid. This separation of electric charge then creates an electric field across the solenoid. The direction of this electric field is opposite the direction of the induced electric field. We can determine the electric potential associated with this separation of electric charge by integrating this electric field across the solenoid. Since the electric field is constant, it can be taken outside the integral. What remains is the path length of the wire in the solenoid. This path length is simply the circumference of a loop of the solenoid multiplied by the number of loops in the solenoid. We can simplify the expression for the difference in electric potential by substituting the expression for the density of loops of wire in the inductor. Part of this expression is the product of the surface area of a loop and the length of the solenoid, pi r squared times L. We can rewrite this collection of variables as the volume of the solenoid. We can then use this result to determine the self-inductance. As expected, the self-inductance depends upon only geometric factors of the solenoid. In this case, it depends upon the volume of the solenoid and the density of loops in the solenoid. This is an equivalent expression for the self-inductance of an inductor. It depends upon the magnetic flux through the inductor and the current associated with the magnetic field that causes that magnetic flux. For the solenoid, the magnetic flux is the product of the number of loops in the solenoid and the magnetic flux through each loop. We can rewrite this expression using the definition of the density of loops in the solenoid. Finally, we can rewrite the result in terms of the volume of the solenoid. We can then use this result to determine the self-inductance. As expected, we arrive at the same solution we obtained before. This is the equation for the magnetic potential energy stored in an inductor. It is proportional to the inductance of the inductor and the square of the electric current in the inductor. This expression indicates that the source of the magnetic potential energy stored by the inductor is the current flowing through the inductor. Mutual inductance is a measure of the ability of a pair of coupled objects to store magnetic potential energy in the form of magnetic fields. Mutual inductance is a function of only the geometry describing the storage of the magnetic potential energy. Objects with large mutual inductance can store more energy than objects with small mutual inductance. A large mutual inductance also indicates better magnetic communication between the two objects. This is the equation for mutual inductance. It depends upon the magnetic flux through one inductor caused by the magnetic field generated from the current in the other inductor and the current in that other inductor. This is the equation for the magnetic potential energy stored through a mutual inductance of two inductors. It arises from the interactions of the current in one inductor and the magnetic potential associated with the current in the other inductor. This energy can do work in the form of driving currents in the inductors. To explore this further, let's consider the system of two loops of wire shown in this figure. The mutual inductance of the two loops relates the flux through one loop to the current in the other loop. If that current is not constant, the magnetic flux through the other loop will change. This change in magnetic flux will induce an EMF. Thus, a change in current in loop 1 will create an EMF in loop 2 through the mutual inductance of the two loops. This EMF will drive a current in loop 2, as expected from Faraday's law. The advantage of knowing the mutual inductance is that it allows for a straightforward determination of this EMF from the changing current without having to calculate the magnetic fluxes. This example illustrates how the magnetic field in one inductor stores energy. When that field changes, it can induce an EMF that can drive an electric current in a different coupled inductor. The magnetic field thus gives kinetic energy to the electric charges in that electric current. Of course, because of feedback in the system, if the current in loop 2 also changes, then an EMF will be generated in loop 1. We'll discuss this further when we talk about AC circuits. Lastly, mutual inductance is reciprocal, so that M12 equals M21. Capacitance and inductance are similar in that they tell us about energy storage. Both capacitance and inductance are functions of only the geometry of the associated distributions of electric charge or electric current. Capacitance relates a separation of electric charge to the associated induced electric potential. Inductance relates a change in electric current to the associated induced electric potential. Capacitance relates a separation of electric charge to the associated electric potential energy. This electric potential energy is stored in the electric field between the separated electric charges. Inductance relates an electric current, or currents, to the associated magnetic potential energy. This magnetic potential energy is stored in the magnetic field of the electric current, or the magnetic fields of the electric currents. The electric potential and stored electric charges in a capacitor can drive an electric current. The induced EMF resulting from a change in magnetic field within the inductor can drive an electric current through mutual inductance.